Yes, welcome to the second talk of today, which is July 2nd. The second talk will be given by Dr. Shaosui Xu, Xu Shaosui, yeah. And you can see her smiling face.
You got it right.
Xu 博士哈, Dr. Xu, she came from mainland China. She did her bachelor degree in the University of Science Technology of China, 中国科技大学 in Hefei, Anhui, huh? And I think you must have graduated from either from physics department or which department?
It's the Earth and I know that the Chinese
Earth and space physics. Earth and space physics.
Yeah.
I knew many old professors there. Yeah. Yeah, and then after the USTC, and she went to Michigan to do her graduate study, and I think you learned many tricks in MHD simulation, right? There, and data analysis, yes. And now she's now working at UC Berkeley as a postdoc. And your boss is what? Is Andrew Pop, or who's your boss?
Actually, no.
You have no boss.
No. I came here as a postdoc like 5 years ago almost, and then became a scientist. So I came here to work on Maven mission. Mostly, I've actually mostly done Mars research, and then started doing lunar research a few years ago.
Yeah, I'm sorry to take you away from the Maven study, which is also very interesting. Only that our program is on the moon.
No. Lunar science is very fun.
Yeah, right. So we would then hear what Dr. Xu has to tell you and what she has learned. And for our young people here, we also learn from her. How the way she learned to do lunar science. Okay, thank you. 徐老师，徐博士，你开始了。
Sure. So I'm going to talk about a little bit more specific aspect of the lunar environment, which is the Lunar Wake Potential Structure. And this is meant to analyze the ARTEMIS spacecraft measurements. And here are me and my co-authors. I should probably have asked, but I didn't know the background, so I'm gonna start with some basic level of introduction. So first, I'm gonna introduce the solar wind interaction with the airless and unmagnetized bodies. One of the example is our terrestrial moon. So to the very first order, especially in terms of the interaction with the solar wind, it can be considered as unmagnetized because there's only very weakly magnetized, very weak crustal fields on the moon. Sometimes I make some Mars. The other thing about moon is airless, or it has a very tenuous exosphere, which results in a very tenuous ionosphere. And because of these properties, at least to the first order, it results into the interaction very unique, simple but unique. So the moon to the solar wind is just a physical obstacle, which means there will be no traditional bow shock like the Marino sheath and all those plasma regimes. And it also means the solar wind plasma have direct impact on the lunar surface soil. And then when you put an obstacle like in the water or something, you will have a wake form just behind the body, and it form what we call plasma void. And then as solar wind passes the body, it starts to refill. So this to the right, we have two pictures, two schematics, shows when the solar wind magnetic field is parallel to the solar wind flow direction versus the flow is perpendicular to the magnetic field. You can see that the for the parallel case, the wake is much more extended. This is a picture like on the textbook. So start with the basic. Of course, the interaction is more complicated when you consider the surface interaction, the crossover fields, and also lots of other interesting phenomena. This just lists a few things, like the surface charging is going to be positive on the day side and negative on the night side. This is something you don't usually consider in other planets with a thick atmosphere. And there's also pickup ions from the moon that generated in the very tenuous but still existing exosphere. You can also have limb shocks formed by the interaction between the crustal magnetism and the solar wind. This is a nice but complicated picture in Jasper Halleker's review paper back in 2011. This just to show the moon's interaction with the solar wind can be very interesting. Okay, so the title is the potential. A potential forms in the lunar wake during the process of refilling. So the like I just said, the wake forms when you have an obstacle in a subsonic flow, and then the refilling produce what we call a rarefaction region. So it spans both inward and outward. And during the process, ambipolar electric field actually set up. So this electric field set up because electron pressure gradient, if you look at MHD equation, or a more conceptual way to think of that is electrons are lighter, they are more mobile, so they can they outrun the ions, so they will form electric field that drags the ions inward and fill the wake. See. Right, so this electric field gives the electrostatic potential in the wake, and this is the topic of this study. So motivation, actually the refilling of the lunar wake has been theorized or modeled since back in 60s or 70s. They started with these one-dimensional expansion theory. And then Jasper did additional study in 2014 to include. So back then they just assumed Maxwellian plasma, and then Jasper expanded that to various plasma distribution, like a kappa tail instead of Maxwellian distribution. And then also there are more sophisticated models like hybrid or particle in cell simulation to simulate the global environment. And then one of them is this ambipolar electric field. And with measurements, people have statistically mapping some of the or many of the lunar wake plasma parameters, like the density, temperature of electrons and ions, magnetic fields, pressures, and lots of things. But they haven't done specifically for these potential structure, because this is not something you can just directly measure. But then Jasper came up with this way to get the potential by compare the distribution function of electrons in the upstream and in the wake. And then that the comparison or the shift in energy gives you the potential that electrons go through. And he did it with a case study. And interestingly, he not only was able to get the potential for that orbit crossing, but then he also find asymmetry in the potential structure for inbound and outbound, which I will show later what that really means. And then he suggests that the asymmetry in the potential structure is caused by the solar stored electrons. So for this study, I'm going to use the 7 years of ARTEMIS data. I did the study like a while ago, so there were only 7 years data back then, to statistically map the wake potential structures and also investigate the causes of the asymmetry in these potential structures. Again, first of all, what I did is go back to the theory. So here is an introduction of the 1D dimension expansion of plasma in expanding into a vacuum, and with assumption of self-similarity. So you start with just one dimension. So this is in space, and this is just the density. For one side, you have plasma, the other side have a vacuum. And as time evolves, the plasma start to refill the vacuum. And then they develop this analytical solution for the potential and also densities and ion velocities. So from especially this equation, what we can get is the potential phi is directly scaled and linearly scaled by the electron temperature, because this is electron pressure gradient terms. So not surprising is scaled by the electron temperature. And the other important parameter we're gonna examine later is the time, which is the expansion time. So that's the time evolve from here to here. But also, as the plasma going along the IMF refill the wake, it also get convected down to the tail. So the expansion time is also a function of the distance from the moon divided by the speed of solar wind. And then the second equation shows you that from the potential, you can also rederive the local density relative to the upstream density. What I did in addition to that is I looked at this 2012 paper where Hutchison actually expanded this 1D plasma expansion to 2D. Because for 1D, you have only plasma on one side, but for 2D, they consider the plasma entering from both sides of the wake. But what they did is analytical solution for the case of magnetic field is perpendicular to the solar wind speed. But when the angle between B and V is not perfectly parallel or perpendicular, which is nominal for a pocket spiral, it will actually introduce a symmetry into the wake potential. So I started to rederive this 2D scenario for this non-perpendicular case, use a similar method in this Hutchison 2012 paper. I think that's actually a single author paper. So briefly to introduce the analytical solution. So this is in the equatorial plane. X is pointing towards the sun, and Y is just opposite to the lunar motional velocity. And then this is, of course, a cartoon. And then for 2D, we divide the whole region into 3 regions. Region 1 and region 2 is where IMF actually intersect the moon. So for these 2 regions, you have plasma entry from only from one side. So you can solve these 2 regions with just 1D theory. And then for region 3, where you do have plasma entry from both sides, and then with the same method Hodgson used, is so we first solve the phi potential for each side with 1D theory, and then from phi we can obtain the density from each side, and then add up these 2 density together to get a total density, and then from density you can rederive the potential again. So what's important about the non-perpendicular case is if you consider a typical IMF, pocket spiral IMF, you can see that the IMF actually intersect the wake at a different distance from the y equals to x equals to 0. That means the expansion time will be different from the 2 sides. And then that different expansion times will give you asymmetric potentials. So this is the complete solution for this a little bit complicated 2D pictures. And then you just use those equations, assume typical solvent condition like solvent speed of 400 kilometers per second, and solvent electron temperature of actually use 24 eV. The typical electron temperature is 12, but that's the core distribution. If you consider the high energy tail, that roughly gives you 2 times of the effective temperature of 12, that is 24. So with these 3 equations, that gives you a potential structure like this. So the color is the potential, and this is a typical X and Y and YZ plane. We can see the potential actually shift to the or more negative in the minus Y direction. Like I said, because the expansion time for the minus Y is shorter than the plus Y. That's why the potential is more negative on the minus Y side. Now we have this theory. Let's go to the data. So I use the electron and magnetic field data from ARTEMIS over 7 years. The way to get the potential from the measurement is to compare the electron distribution function in the solvent, which is the dashed lines. They are separated for different pitch angle distribution. So parallel, perpendicular, and anti-parallel. And then if you compare that with electron distribution in the wake, you see the shift in energy. This doesn't look like a constant shift because the x-axis is in the log scale. But if energy is in linear scale, you will see this is a constant energy shift, which gives you the potential that electron go through and get decelerated. So that's the main methodology we get the potential. And also, since we can calculate the potential from electrons in either direction, parallel or anti-parallel, but we actually select the results from electrons going from upstream to the wake. It's just more reliable. And of course, we are looking at the case where the ARTEMIS and the moon is in the solar wind, and also we constrain that to a steady IMF condition. So this is more data filtering criterion. So this is an orbit example of ARTEMIS measurement. This is location, magnitude, there's some magnetic angle and spacecraft potential, ion energy spectra, electron energy spectra separated for parallel and anti-parallel direction. And the last panel is the potential we derived with the by comparing the electron distribution function with electrons going from upstream to the wake. So you can see, so it starts with each side separately. First of all, you can see this is what we expected. The potential is roughly 0 outside the wake, and then goes down to minus 200 to 300 in the center. But what's more interesting is this disparity at the center of the wake. This is also what Jasper reported back in 2011 with a case study. And then he theorized that this disparity comes from the asymmetry in the solar wind electron distribution. So this is a solar wind distribution in velocity space. So this would be V parallel and V perpendicular. The color would be the flux or distribution function or phase space density. So you can see mostly the distribution is isotropic, except for when there are high flux straw in one direction, mostly flowing from the sun to away from the sun. And then because of so that means you will have high flux in one direction. In this case, is in the parallel direction. Fluxes are higher for parallel electrons than the anti-parallel direction. So that gives you effectively higher electron temperature on in this direction than the other. So that can cause a asymmetry in the potential as well. And another interesting thing about this orbit is that there are reflected protons in the wake, and while that occurred, we also see some reduction in the potential as well. So this is just an impact of reflected protons on the wake potential too. So with that, we had an automated procedure, and I ran that for 7 years of ARTEMIS data, and then get all the potentials. For the statistic analysis, I rotate the frame such that the X is in anti to the solar wind flow, and the Y is the same as the IMF direction in the flow. It's along the IMF. It can be parallel or anti-parallel, but the important thing is plus Y is always having the leading end of IMF, and then the minus Y is the trailing end of IMF. So this will preserve the Parker spiral IMF. And also an advantage of that is the stored electrons will always go from minus y to plus y. Okay, so with this frame, we can look at some parameters. So these are the potential mapped in the XY plane, but separated for high electron temperature and low electron temperature case. You can see the potentials are more negative for high electron temperature. Or if you collect all the data within this box and plot the potential as a function of electron temperature, we can see this linear scale of potential with electrons. So higher electron temperature, either you can think of that gives you a higher pressure gradient, or there are more electrons at higher energies to putting ions towards the wake. This is a more conceptual way to think about how electron temperature changes the potential. The other parameter we can study, or I studied, is look at the solvent speed. Again, potential in XY plane for fast and slow solar wind. Again, for fast solar wind, first the wake is more extended, and then also the potential is more negative. One way to think of this is with a higher solar wind speed, for the same given time, IMF will convect it further down tail, so that makes the wake is more extended. And for the same, or if you look at the same x distance, there's less time to refill, and the wake is more depleted, which gives you a larger phi as well, or more negative phi. Another key point of this paper is to study the asymmetry in the wake potential. I don't know if you recall, but there are two reasons that can cause the wake potential. One is the stored population in the solar electron distribution, which can cause asymmetry of or different electron temperature on two sides of the wake. The other is this non-perpendicular IMF case. So we are going to examine them separately. So first one, if we confine the case where IMF is mostly perpendicular to the solar velocity, so take out the factor of non-perpendicular IMF, but then look at cases where there are stored electrons versus no straws. We can see the wake potential is more asymmetric for the case with straw case versus a more symmetric case for non-straw case, because the solar distribution is roughly asymmetric for the two sides of electrons. So this confirms Jasper's finding. And the other one is if we take all the cases where the solar electron distribution is more or less symmetric, and then just examine the angle between solar velocity and IMF. So here is a close to perpendicular case, and this gets more and more parallel. As we can see, for the this is like the ideal simplest case where everything is symmetric. But then as IMF gets more parallel to the solar speed, the wake potential structure gets more asymmetric. And of course, like we introduced at the very beginning. When B is more parallel to V, that gives you also a more extended wake as well. So with the data, we can statistically prove that yes, the asymmetry in the solar electron distribution can cause asymmetry in the wake potential, and also the angle between V and B can also cause the asymmetry, just as the 2D formula predicted. This is a little bit more discussion on the asymmetry. If we take slide through this region and plot the potential as a function of y-axis for straw, to look at purely straw effect, the no straw and also perpendicular IMF, and also the effect of non-perpendicular IMF. One interesting thing is this is the ideal case where everything is symmetric for the plus and minus y direction. So the tilted IMF, it causes just the minimum potential just shift to the minus y side, but there is no net or potential jump at the center. If you compare that to the straw case, actually you will see a potential jump at the center, which is physical. Unphysical. We don't expect there is a large potential jump at the center. Rather, it's more likely that the so all the potentials are relatively to the upstream, where we specifically use the distance of 1.3 to 1.5 from the obstacle shadow, or the distance from the x-axis. So that just means it's more likely that our zero potential is not the real zero potential. So it's more likely that we shift this distribution downward, and then you end up with a non-negative potential here, and slowly goes down to zero at a far distant location. So we interpret this disparity as effect of as indication that the wake effects can extend further into the upstream than we previously thought. So this is a really interesting point about two different factors might affect the asymmetry in different ways. So lastly, we have the model, we have the data, and then we can do the direct comparison of the potential. So this is the case where the IMF is more or less Parker spiral-like, and then I use the same median IMF direction for the model. So this is the potential comparison, and then this is the relative difference of these two. So what we can see here is the potential is mostly 20% difference in most of the wake region, except for when it's very close to the moon. So a couple of possibilities. First of all, this is where the potential is most negative. That means hardest for electron to penetrate, or you have to have very high energy to get into this portion of the space. So its model can easily under predicts the phi in this region because we just use the electron temperature of 24 volts, where in reality, the effective temperature is going to be much higher once all the low energy electrons being filtered out. So it's no wonder that we get a much shallower potential from the formula. Another possible reason is that this is also the region where it's obstructed by the moon, which means the IMF is connected to the moon. So the interaction with the lunar surface might be important and result into the difference between data and model as well. Okay. Another thing we did is we take the averaged potential map, and then you can calculate the electric field by take the gradient of the potential. So the color here shows the absolute magnitude of the electric field, and then the arrows shows the direction. The top one is the data, and then the bottom one is the model. I believe is correspond to these two potential maps. The electric field on the minus y side have a decent agreement, but we do find a significant difference on the plus y side, just because the potentials are very different on this side as well. But the magnitude of the electric field are in general in good agreement, roughly on the order of 0.1 millivolts per meter. If we look at a hybrid model, just look at, this is for a perpendicular case. If we just look at the magnitude, the ambipolar electric field from hybrid model also have agree in magnitude with our data, simple 2D model, and also data, just roughly. Okay, so just a few key points to summarize the talk. So first of all, we developed a 2D analytical model for the wave potential for the case where MF is not perpendicular to the solvent velocity. And asymmetry can develop because of the expansion time going to be different for plus and minus y when IMF is not perpendicular. And then we statistically map the wave potential structures with ARTEMIS data for the first time at high altitudes. There's some words I should use. And then we did some parameter study that shows a good agreement with the theories as what we expected. And then especially the comparison of data and our 2D model, we find a decent agreement as well. And lastly, the straw effect can cause a net potential difference across the wave, which suggests potential can extend further into upstream than previously thought. I actually have an extra slide, which doesn't belong to this study, but we did actually did a follow-up study of the reflected proton in the wake, how it impacts the wake potential structure. So long story short is when the local reflected proton density is comparable to the local solvent density, the wake potential can be significantly affected. You can even use logarithm. There actually quantitative relation between the two. The wake potential scales as the logarithmic density of the reflected proton in the wake. So this is actually a very nice, neat follow-up study of the first one. So yeah, that's all. Thank you.
Yeah, thank you so much, Dr. Xu. I think very detailed description. I think you have done a very good work. Nice job. And the ARTEMIS data set is it's beautiful, and your analysis is very detailed. And any questions from the audience? Nishino-san, are you there? Nishino-san?
Yes, I'm here.
You want to ask Dr. Xu a question in Mandarin?
Hi.
Yeah, actually, I enjoyed your talk very much, and your papers, recent papers as well.
Thank you.
So
long time no see.
Just let me confirm one thing. You to find the potential inside the wake, you compare the electron data from probe 1 and probe 2. Is it right?
Actually, I didn't do something sophisticated as that. It's more so that I take the each probe independently, but find times when each probe is in the upstream and then inside the wake. So there is a time difference between the two, and we just assume the upstream electron distribution are stable.
Okay.
Yeah, I guess at the beginning I wasn't used to think about, oh, we actually have two probes. Yeah.
In one of the slides, you compared your data with the model. Look very nice. However, I want to know, because in your data, you have those distribution very close to the lunar surface. And how did you manage to go? Because ARTEMIS did not go really that close to the surface of the moon, right? Like this, like this very, like those the blue part, that is very close to the lunar surface. Am I correct, or am I mistaken something?
You can see my slide, right?
Yes, I saw it. Yeah.
Okay, good. I was confused what you are saying. So first of all, ARTEMIS periapse can be down to 100 kilometers. But the reason why you see pixels so close to -1 is because this is a slab of plus minus 0.5 lunar radii, and then projected in this XY plane. So yeah. So that's why it looks like it's within the -1. Yeah.
So the model you refer to is from whom? From ARTEMIS or from?
You mean this one?
Right, this one, yes. And is that you did it yourself or?
Yeah. So this is So this Hutchison paper, he derived this 2D analytical solution, but for case B perpendicular to V. So I just follow their step, but but the solutions are slightly different because the geometry are different. It's a bit more complicated.
Okay.
Yeah, I think we actually talked at meetings, and he probably saw me presenting the other study on the how the reflected proton in the wake affecting the structure, the potentials.
Because in one case you saw that there's a bump in the data because you said that time you see the reflected protons, right? Right. This one.
Yeah.
And do they come as a beam or come as just a like a surface? Those reflected ions.
It actually can be lots of dispersion because the reflection is can at any angle when they gyro into the wake. They actually can be in all directions. Usually, you see that in all directions. Yeah.
Okay. Of course, this is a big discovery of Nishino-san. And anyone want to ask? Take this chance, to ask Dr. Xu a question, because this is a really, very nice, detailed job.
Yeah. Hi.
Hi.
Long time no see. Maybe you did not remember me, but
yeah, I cannot see.
You remember me. We met at Berkeley Space Science Lab through Joanna in 2019 when I was doing the coffee project. Yeah, I have no question. I just want to say hello to you and hope you and Joanna are well and fine and safe in Berkeley.
Oh, thank you. We are trying to survive during the pandemic.
Okay, and thank you for sharing your experience for the Lunar. Yeah, thank you.
And
thank you for listening.
Anyone? Professor Nakagama, you want to ask Dr. Xu a question? Yeah, Professor Nakagama.
I have just entered the here just because we had the entrance examination of our graduate school, so I just looked up the last slide, only the last slide I saw.
Okay, so Dr. Xu, you have to repeat the talk again.
Yeah, in less than 10 minutes.
Yeah, Dr. Professor Nakagawa gave a talk a few days ago, and it was also very, very good. I think actually I was thinking afterward. Just last night I was thinking that to ask Professor Nakagawa to give another talk again, mainly to go into some detail. Some part of your lecture, even though it was 1 hour long, but that you cover so many things. There must be some specific, a phenomenon that would be worthwhile, to basically to explain, more about the physics of plasma waves. Could we do that, Professor Nakagawa?
Yeah. By the way, today's talk looks very interesting because I was also interested in surface charging and surface potential. So it looks very interesting.
So besides, I want to ask Dr. Xu, besides this paper, have you worked on other things on the moon?
Yeah, so the follow-on is the impact of reflected proton on the wave potential. And then this year I published one on, we tried to use the photoelectron measurements from the moon. They do exist. And then we actually can find the oxygen OJ electrons in the electron distribution. So that's a really nice thing. We try to use the electron measurements to derive the surface yield, but then it turns out to solve that complicated equation, we need another thing that's like no one measured since 60s. People just assume what they call the probability function. It's just assume the probability function. And so without that, it's hard to...
Go ahead.
Yeah, without that probability function, it's hard to derive the yield. Yeah, but it's just tells you that we really, if we want to know the photo emission yield, which is important for the surface charging at high energies, we actually need to do experimental work, more experimental work to get this accurately determined, and then people can put that into their model for a better estimation of surface charging.
Yeah, I just was wanting to say that what you're doing, also what the Professor Nakagama doing with the plasma waves is very much, the 100% pure plasma physics, but in a space environment. So that's very, very interesting. Yeah, very basic research. Do you agree, Professor Nakagama?
Yes, sure.
Okay, so both of you have to give another talk. That's the main thing. One on photoelectrons, right? And then Professor Nakagawa, I have to and write to me when you think that, from the point of view of clarifying some things that you are think that for plasma wave generation instability, important thing that because we have already this a set of lectures, videos. So then we can afford to go into more detailed discussion. Yeah. But given 45 minutes and an hour, I think it's a good time to really discuss to describe something in detail. Usually you could not do that at meetings, right? Yeah. But then here, give us the platform. Yeah, and also very good for students, because they could come back and look at your your video and so on to understand more. Okay, I think that any other questions from other audience? I want to say hello to Dr. Xu.
Yeah, actually I have.
Yeah, please.
Yeah, good morning to everyone. Myself Imran Chaudhary, I'm from India. So actually I joined at in the last of 10 minutes of this event. So my question will sound dumb to you guys. So sorry for that, but I wanted to know that what is the application of this whole thing, what you presented, like the post-process data you were showing, that was very that was very raw and genuine, I think so. So I was not able to I was not able to find what kind of application we are getting from this finding.
This is a hard question, a challenging question. Dr. Stewart, he was asking you what is good for with your study, right? Am I right?
Right. The significance, the one thing you always have to answer. So it's more like about the better understanding how the interaction of the moon with the solar wind, because I mean, the great things about planetary research is you have different planets with different magnetic and also different characteristics, like magnetized or not, with atmosphere or not. And to the moon is one type. And then it's always good to understand one type of interaction to better understand other types of interaction. At least from my perspective, I've been doing Mars research for a long time. And then when I start to do lunar research, and then you kind of have a better understanding, or just give you a different view of how the different planetary environments can be different in terms of interaction with the solar wind. So long answer short is this is not something like directly connected to like a manned missions or landers on the moon, those kind of things. But this is one of the basic but also fundamental aspect of the interaction of the moon with the solar wind?
Yeah, I think for me, what it tells us is something like going to new places where no one have been ever before, no one have studied before, and then you realize that that's what humans are made for, to carve more or less to overcome the challenge, right? To say, oh, it could be done, I could use my what I have learned before, the basic physics, and I could understand, solve the problem. And then you have more, you have this experience, and you have more confidence in doing other things, and exploring other new things.
Yeah, and also it's more like you have the same set of equation, but your conditions are different for different planets. That gives you very different results. That's one thing always fascinating, or makes me fascinated about planetary research. You have all kinds of natural laboratory to explore different types of interactions. So, very
good. Thank you so much again, Dr. Xu, and have a good night, good evening. In Berkeley. Yeah.
Yes. It's 8 o'clock.
It's still 8 o'clock. Yeah, it's the night still young, so you could still write paper. Okay, thank you. Bye-bye.
Bye.